Hello again. In this video, I want to discuss the Helmholtz coil configuration. So this is a way of producing very uniform magnetic fields. The first observation I want to make goes back to, I don't know, I suppose it's algebra or something. Namely, if you have a function, and let's say it has some sort of a graph. Okay. If you want to push the graph forward, then you must subtract from the argument of the function. Similarly, if you want to pull the graph backwards, you have to add to the function. Okay, so with that observation, what we want to do is study two coils, each with interns, and we want them to be separated by a distance L. And because each will have many turns, I'll say I have Ni turns here and Ni turns there. And Ni gives me the total current around this loop, because each wire carries current I and you have N wires. Now, to build this situation, going back to just a single loop, we found the formula for the magnetic field above the center of a single loop centered in the XY plane. So to get two loops, one up and one down, so I'm going to put Z equals 0 in the middle. What we need to do is simply take our previous formula and shift the result up to get the top loop and shift the result down to get the lower loop. So the magnetic field total is simply going to be the magnetic field of the top plus the magnetic field from the bottom. And that's easy enough to accomplish. If we put 0 here, then this must occur at Z equals L over 2, and this must occur at Z equals minus L over 2. Those two amounts tell us how far to shift things. So the formula for this must be mu naught times mu vector divided by 2 pi, and then I must have 1 over Z minus L over 2 squared plus R squared to the 3/2 plus 1 over Z plus L over 2 squared plus R squared. So you can see here, this is from the top coil because I've subtracted from Z, which has the effect of moving the loop up. And over here, I've added to Z, which has the effect of moving the loop down. And that's the full answer for the Helmholtz coil. However, it doesn't really explain why this particular configuration ever might be useful. To do that, I'm going to expand out some of these denominators. So look and note that for Z close to 0, it doesn't have to be exactly 0, but just close to 0, and we're going to keep the leading terms here. When I write this out, I would get Z minus L over 2 squared plus R squared. And that is, to good approximation, L over 2 squared plus R squared minus LZ. There's another term here which goes like Z squared, but if Z is small, these are the dominant terms. And similarly, Z plus L over 2 squared plus R squared should be pretty close to L over 2 squared plus R squared plus LZ. All right. So in my square, or in my formula there, I get 1 over, and I have R squared plus Z minus L over 2 squared to the 3 halves. You just need to work out the Taylor series for that and keep the first terms. And that's going to be pretty much 1 over R squared plus L over 2 squared to the 3 halves times, and you get 1 plus, because this is a negative shift in the denominator, which makes the overall thing grow. So that's why you get a plus piece, 3 halves, and then you get LZ over R squared plus L over 2 squared plus higher order terms. Similarly, 1 over R squared plus Z plus L over 2 squared, 3 halves, will give you 1 over R squared plus L over 2 squared, 3 halves, times 1 minus 3 halves LZ over R squared plus L over 2 squared plus other terms. Great. So let's go back. That's a lot of mess. So look what we have. We have this prefactor, and then we have to add these two terms. Well, look what happens when you add these two terms. The prefactors are the same. The ones add up to give you a factor of 2, but these two terms, the leading dependence on Z, actually cancel. That's the big deal. The Z dependence is softer than you would generically expect. Generically, you expect a constant plus a linear term. Here, the linear term cancels in the Z direction, and so you get a magnetic field which is quite uniform in the Z direction. So the magnetic field is, for small z, going to be mu naught times mu over 2 pi, that was the prefactor, divided by R squared plus L over 2 squared, so the 3 halves, times, when you add them together, you get 2. The linear term cancels, and then you do, in fact, get some order z squared term, but it's much smaller when z is small. So this becomes approximately constant in Z. So this can produce nice uniform magnetic fields. So let's take a look at what we actually see from an image I found on the internet. And here you go. This is a Helmholtz coil configuration, and you'll see very nice, steady, uniform magnetic fields in the interior. Nothing is changing as you move along the axis of the coils. You might have noticed I have coils like this in the room, and if we were in person, we would use this to do an experiment to measure the charge to mass ratio of the electron. So anyway, that's what this image is actually from here on the right. Okay, let's go back. All right, so that is the formula for the Helmholtz coil. It's a famous configuration. It's not that bad actually to work out. It's easier than a straight wire. Notice the currents here flow with the same sort of handedness. If it was oppositely oriented, then what you would find, in fact, is that the leading terms would cancel, the two would go away, and then the linear terms would actually add up. And so that would give you a different kind of, that would give you a roughly linearly increasing magnetic field, which maybe that has another, that might have other applications. All right, in the next video, I'm going to discuss how, or what a solenoid is, and how to obtain a formula for the magnetic field in the center of a solenoid using Biot-Savart.